All right, in this section, we're going to look at two tests that are non-parametric. Again, we won't be able to rely on mu or sigma. And so these ones are referred to as the Wilcoxon tests. Let me start with the first one. The Wilcoxon signed rank test is a non-parametric test that is used to determine if two populations have the same distribution. All we need is a random independent sample. So let's go over the steps performing the Wilcoxon signed rank test. What are those steps? 1, verify that the samples are random and dependent. Up top, I made a mistake. I said independent, but what I really wanted was dependent. So we need a random sample that is dependent. What are you talking about? They're going to come in pairs in this test. Specify H sub 0 and HA. List alpha. Determine the sample size N, where we ignore zeros, sort of like what we were doing before. Use the Wilcoxon signed rank test table to determine any critical values. Compute the test statistic WS. Now it's a little bit different than the ones we did before. I don't actually have a formula for you, but the way we'll set up a table like the following. We'll set up sample 1, sample 2. This will be a paired sample, as I mentioned. And then what we're going to do is create a column that is the difference. And then we're going to take the absolute value of that difference. Then we're going to rank them. and then we're going to assign assigned rank to each entry. And it's when we get to the assigned rank that we'll finally be able to figure out what the test statistic is. Let me call that part A. Part B of this process will be to compute the sum of the positive ranks you want to compute the sum of the negative ranks then select the ranking that has the smaller absolute value. Finally, make the decision. Okay, in this example, this is a perfect example to start this process off. What we have here is a quality control inspector wants to test the claim on their spray on water repellent. They want to see if it's effective or not. So they're spraying it on fabric, and then they're measuring the amount of water that comes off of the fabric. So the more water that comes off, the better the repellent is. So let's see what they want. Can he conclude that the water repellent is effective? If it's effective, that means that the amount of water that came off during the no repellent is less than the amount of water that came off with the repellent. See, look at this. No repellent had less water that came off than the repellent does. So we expect there to be something different. I don't know that it's going to be better or worse, but I expect it to be different. So this is the way it can look. For this, we can just say for HA, we can say the repellent is effective. So in HA, when you say the repellent is effective, you expect that the amount of water that comes off to be different than initially without the repellent. So the H sub 0 then would say the repellent is not effective. Basically here you're saying that the amount of water that came off when we had no repellent was the same as the amount of water that came off when we used a repellent. So in other words, they're equal. That's why it goes into H sub 0. Anyways, let's go ahead and make up the table that I was suggesting for you. Let's do, I think I'll do it this way. I'll do no repellent, and then we'll have a column for repellent, and then we have their difference, and then the absolute value of that difference, and then we have a rank, and then assigned rank. And let's put, first of all, the easiest thing to do is to plug in the numbers. So let me put those in for the no repellent. 8, 7, 7, 4, 6, 10, 9, 5, 9, 11, 8, 4. And now look, let me put in the repellent numbers. Here we have 15, 12, 11, 6, 6, 8, 8, 6, 12, 8, 14, and 8. All right, so I don't need that information anymore. Now I'm just going to start building up the table. First thing we want to do is take the difference. So 8 minus 15 gives us negative 7. Moving on to the next item, 7 minus 12 gives us negative 5. And just keep going. As you can see, generally speaking, it looks like the repellent does yield more excess water than without it. All right, so I got all my differences. Now I'm going to take the absolute value of every difference. This is a very simple thing to do. All you essentially do is turn the negatives into positives. All right, when we do the rankings, what we want to do first of all is forget about the zeros. We don't rank the zeros. Now we're going to start the numbers themselves. We have rankings available 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n equals 11. So what I want to do is I want to rank 1 through 11, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these are the ranking spots that I want to use, but the way it works is complicated. Look at the rankings for 1. You see the number 1 here in the absolute value is repeated. Well, what we want to do with that then, instead of assign one of them a 1 and the other one a 2, we want them to be equal. So one of these has rank 1 and one of these has rank 2. What we do with those is we take one of them has rank 1 and one of them has rank 2 and we divide by 2. And I end up with 1.5. So I'm going to put 1.5 next to the 1s. So what I've used are rankings 1 and 2 for that. Now I get to use, now I'm up to 3. Now let me look at the next item in our list. I've got a 2, but I also have a 2 again. So these 2s are going to use up rankings 3 and 4. So 3 plus 4 divided by 2 equals 3.5. Let me mark these off. So I'm going to put a 3.5 next to the 2s. All right, moving on. My next number on the list is 3, and once again we have a repeat also. So the 3s are going to use up 5 and 6. 5 plus 6 divided by 2 equals 5.5. So I'm going to put a 5.5 next to the 3s. All right. Moving on to the 4s. How many 4s do I have in my list? I have 2 4s in the list. So I'm going to use ranking 7 and 8 for those. That is equal to 7.5. So the 4s get 7.5 next to them. You need to keep track of the rankings that you have left as you go. Now, my rankings that I have left are 9, 10, and 11. Let's take a look at the 5s. How many 5s do I have in my list? Wait, I put a 7.5 next to the 4. Get out of there. Now my ranking 9, since I only have 1 5, I'm going to put a 9 next to it. Mark it off. All right, ranking 10, we'll go with the 6. And then ranking 7 will get 11. Now for the signed rank, you want to pay attention to whether the difference was negative or positive. So look at this negative that is the 7. I don't care about the 7 part of it, but I do want the negative part of it. So I'm simply going to call the signed rank negative 11. And as I go through this list, anything with a negative, like this negative 5, I go across to the 9, and I'll assign its rank negative 9. There's a negative there, so that makes this negative 7.5. Moving on, there's a negative here going across. That makes this negative 3.5. Here we finally get a positive one, so this will be a regular 3.5. These ones all positive, so this will be 1.5. There's a negative for this row, so that's negative 1.5. There's a negative there, so negative 5.5. This has a positive here, so this is a positive 5.5. Negative right here makes this a negative 10. Negative here makes this a negative 7.5. So I finally finished my table. Now what we're going to do is add up the negative terms and the positive terms in the last column. So add up the signed rank column, but add the negatives together and the positives together, and then compare their absolute values. So here's what I mean. Let's add up. So we're going to do the sum of negatives. I'm going to use a notation that I don't think is used anywhere else. I'm going to call it W minus. So I'm going to go through the list and put all the negatives down and add it all up. So that list, almost everything in that list was negative. So I see in my signed rank column, I have, so this is the column that I'm looking down, and I'm going to add up all the negatives first. So I'm going to do negative 11, minus 9, etc., etc. So let me go ahead and get those things down. We had negative 11, minus 9. Then we had negative 7.5 and negative 3.5. Let's see what else we had. I think I've got the first four okay. Then we have negative 1.5, negative 5.5. Then we have negative 10 and negative 7.5. So let me add up all of these numbers. Whatever screen you're in, quit it. Let me move this thing out of my way. All right, for the initial negative 11, don't forget to push this little negative button. For the rest of it, you can use the minus button. So I get negative 55.5. Let me write that down. Got it? Now I'm going to add up the sum of the positives. So I'm going to call this W plus, and let's see what those numbers are. Once again, I'm looking at the final column, the signed rank column, and I only have a few items in here for the positives. I have 3.5, 1.5, and 5.5. Now what you also need to do is I'm going to count these items to make sure I've accounted for all 11 of the non-zero items. So here I had 1, 2, 3, 4, 5, 6, 7, 8. And down here for the pluses, I have 1, 2, 3. 8 plus 3 is 11. So I accounted for everything. Now this is equal to 10.5. Now our test statistic, which we call W sub S, is equal to the minimum of the absolute value of W minus or the absolute value of W plus. Now the plus the absolute value doesn't matter because, well, the absolute value of a positive number is still positive. So I'm going to do the absolute value of W minus, that was negative 55.5. And the other one was 10.5. So before I do this, let me take the absolute values of each of them. So I'm comparing 55.5 and 10.5. The minimum of those two numbers is 10.5. So this is my test statistic. All right, now that we found our test statistic, let's use our alpha equals 0.01 and n equals 11 to find our critical number. Let me come back to the H naught and HA. I think that when I did this, not effective or effective, I guess I misinterpreted a little bit. Let me put this. The amount of water repelled is more. So what do I mean by that? If we look at the amount of water before, it should be less than the amount of water that's after. So the amount of water, I mean, that comes off of the fabrics. So I guess the way I said it originally, a one-tailed really, or two-tailed wasn't really true. For the first one, I would have my before would be greater than or equal to the after. So we can see that this is a one-tailed test. All right, sorry that I did that. Now come back down to where we get what we're doing, because it's going to make a difference whether it's one or two-tailed. So this is a one-tailed test. And let's go ahead and take a look at my table. All right, so I'm looking at one-tailed and I see alpha equals 0.01. Now I'm going to scroll down until we get to n equals 11. So we can see that this here, this 7, is the critical number. So I'm going to call it W sub 0 equals 7. Now remember the way these tables work a little bit opposite the way we're used to. Here, since W sub S is greater than W sub 0, since 10.5 is greater than 7, we do not reject H naught. Now, I don't have any kind of a calculator shortcut for any of this stuff. There's nothing built into the calculator that can handle this, but none of the computations are very difficult anyways. So, well, let's move on to the next test. Definition. The Wilcoxon Rank sum test is used to determine if two independent samples come from populations that have the same distributions. So what we have then is the sign rank. We want dependent samples. And for this one, rank sum, we want independent samples. It should be fairly obvious from the things that they're comparing whether the samples are independent or dependent. Now, in addition to the random sample and all that, we need, for the rank sum test, we need n to be greater than or equal to 10. Keep that in mind. Now, it's going to use the normal distribution. It will be normally distributed with this. Z equals, this will be our test stat. And it will look like this, R minus mu sub R divided by sigma sub R. So it takes that standard normalization process. It looks very similar to it. And let me give you the formulas for the R, mu, and sigma. R equals the sum of ranks for the smaller sample. So you're going to have two samples. They're going to be independent. It's possible that they have two different sizes. What I'm saying is this R will refer to the one that has the smaller size, if that's the case. If they have the same size, then it won't matter which one we're calling small and which one is large. They're both the same in that case. You'll see as we do an example. And then mu sub R looks like n1 times n1 plus n2 plus 1, all of that divided by 2. And then sigma sub R is the square root of n1 times n2 times n1 plus n2 plus 1, all of that divided by 12, and all of that is inside of the square root. We need n1 to be less than or equal to n2. Let's do an example. All right, let's take a look at this example here. Let's see, can you conclude that there is a difference? That's what I'm interested in. So whether there is or is not a difference. So for HA we have there is a difference between the payouts of company A versus company B. So that would be like a non-equals, if you will. And then we have there is no difference in the payouts. So those are our H0 and HA. Here I have two samples. We can see that they should be independent samples. Next, what we want to do is we want to arrange the data from lowest to highest, and it's going to be all one long string. I'll show you what I'm talking about here. So what we're going to do is put, well, let's just put down the numbers. I'm going to put 6.2, 10.6, 2.5, 4.5, 6.5, 7.4, I'm taking care of company A first, 9.9, 3.0, 5.8, 3.9, 6.0, and 6.3. And then for the other one, let me get these numbers too, 7.3, 5.6, 3.4, 1.8, 2.2, 4.7, 10.8, 4.1, 1.7, 3.0, 4.4, 5.3. Now what you should do is make this into one long string of numbers sorted from lowest to highest. Now I personally, you could probably start writing them and crossing them out as you use them. So the list that I want, let's start with what I think is the lowest, and what looks like the lowest to me was 1.7. So let me say this was A and this was B. So what I want to do is this. Let me put my 1.7 here and then list the company that it was with. 1.7 was a company B. So let me mark it off. I've used it. Now let me find the next smallest, which was 1.8. That also looks like a company B. Let's see what's next. 2.2. That was a company B. And then let's scan through and see what we have next. I think I see a 2.5 here for company A. Got it. Next, I see a 3.0 for company A. And I see a 3.0 for company B. So I got that one. After the threes, I see a 3.4 for company B. And then after 3.4, I see a 3.9. Let me see if I can find it. 3.9 for company A. After that, I've got a 4.1 for company B. And then I have a 4.4. Where are you at? 4.4. There it is. That was company B. 4.5. Where was 4.5? That was in company A. Moving on. 4.7. Where was that located at? 4.7 was in company B. And then we had 5.3 in company B. And after that, I have 5.6 in company B. And then we have 5.8 in company A. I had a 6.0 in company A. After that, I have a 6.2. Where was that at? That was in company A. Then I have a 6.3. Still company A. And then after that, I've got a 6.5. 6.5 is in company A. And then I have a 7.3, which is in company B. After that, I have a 7.4 in company A. Then I have a 9.9 in, I took care of that 6.2, let me cancel it. 9.9, where are you at? There it is, company A. And then 10.6 was company A. And then I had one last one, which that's 7.3. Let me see if I had checked that off. I had not marked it off, so let me mark it off. 10.8 came from company B. Now, just by looking at these, you can see how A dominates the higher numbers and B dominates the lower numbers. So at least according to this, it kind of looks like that A is doing higher payouts than B. But we're not looking at a one-sided test here, or one-tailed test. We're looking at two tails. Now what you do is you rank all of the data. So let's go ahead and do that. So let me put our rank over here. Organizing it is crucial for this ranking. That'll be 1, 2, and the only time you have to worry about 0.5s is when you got things that are equal. So the next one is 5. So the next two spots should be 5 and 6. But if you take the average of 5 and 6, you get 5.5. So that was 5, 6. And now I'm going to move on. 7, 8, 9, 10. I don't know if we have any other ties. If not, then I can just count. So I've got all of my rankings. Now what you want to do is look at the rankings of A versus the rankings of B. Both sample sizes are the same. If you notice, we've got no zeros to worry about here. We have that the total sample size is 24, and each of the samples is 12. So in this situation, it doesn't matter which one's smaller because they're equal to each other. So what I'm going to do is I'm going to gather up all the rankings for A and let them represent N1 material. So let me look up all the A's. There's 1, 2, 3. So I'm using Company A as sample 1. Company B will be obviously sample 2. So let me add up those ranks for column A. That's because Company A had the smaller sample size. I know they're equal, but we had to pick one of the sample sizes. So I'm doing this for the smaller sample size. So R will be what we use, and I'm going to add up all of those numbers. So let's see what all the numbers that were involved with A. I had 4 and 5.5. And then after that, I had 8 and 10. And then I have 15, 16, 17, 18, 19. I made a mistake here. That's 22. Then I have 21 plus 22 plus 23. And this turns out to be 179.5. Now mu sub r is very simple. That's n times n1 times n1 plus n2 plus 1 divided by 2. And here n1 and n2 are both 12. And so that is 150. And then for sigma sub r, we have n1 times n2, n1 plus n2 plus 1. All of that stuff is divided by 12 on the inside of the square root. So I'll have 12 times 12 times 12 plus 12 plus 1 divided by 12. I'm just a little simplifying. I notice that I can cancel out these 12s, and it looks like I'm going to have 12 times 25. And I believe, well, let's go ahead and get that number. I just want decimal, maybe 3 decimal places for it. So let's turn it on. Take the square root of 12 times 25 and enter and see what happens. So 17.321. So don't forget that was sigma sub r and this was mu sub r. So I've got everything that I need. Now let's go ahead and calculate the test stat. And here we're going to use z, so you know it's going to be the normal table that we're going to use for our critical numbers. That's r minus mu sub r divided by sigma sub r. And my r, where did you go? 179.5. Mu sub r is 150. Sigma sub r is 17.321. And let's go ahead and get the approximate value of this. And you can do it all in one shot on your calculator. You can do 179.5 minus 150. Finish the parenthesis and then divide. If you wanted to, you could be really cute about this and write second answer, and I don't have to type in the 17.321. And let's see what we get. I get about 1.70. You only need to go 2 decimal places here because the table only works to 2 places. Now for the critical values. Here, let me see what alpha was. Alpha was 0.05. So alpha over 2 equals 0.025. So what we're looking at is a two-tailed test, remember. So I want 0.025 over there, 0.025 over there. Let's get these numbers. Once again, you can use your calculator for this or you can use the Z table. I am going to go to distribution, so second, distributions. I want inverse norm, so I want 3. I'm going to go for the left end point, so I'm going to point 0.25 will be my area. Leave the rest of it alone and see what we get. I get negative 1.96. That means over here I have 1.96. When I look at my test value, it's right there, and that tells us that we are not in the critical region, so do not reject H naught. All right, here I have an example that I want to use one of the tests for. So these ones are not meant to illustrate one of the other tests, but you need to decide which test to use based on the material that you're given. So let's first see what this says and then see what we have to write down. Let's write our H naught and HA down. We have a private industry analyst claims there's no difference. So this is a two-tailed test. There's no difference. So our H naught, we'll write something like there is no difference. So you can think of that as being an equal sign if you'd like. There's no difference in the salaries earned by the workers in the wholesale trade and manufacturing industry. So there's no difference in the salaries of wholesale workers versus manufacturing workers. So then HA would be there is a difference. in the salaries of the wholesale workers versus the manufacturing workers. Let's decide on which of the test is more appropriate. Here, it's not like a before and after, and there's not any necessary connection between wholesale and manufacturing. So these, to me, look like we have independent samples. With independent samples, we want to use the rank sum test. So with that, what we do is we list all of the numbers in one long column, then we organize them, and then we start doing the rankings. So what I'm going to do is something slightly different than last time. I personally think it's a hard thing to do to organize numbers as you go unless you mark them off from up here. And so I think maybe that's what I'm going to do. So we're going to put them in order. I don't know why I brought out the calculator. I was going to have the calculator order them, but I don't think I need to anymore. So now what we need to do is look through all of these numbers and see what our lowest number is. And to me, it looks like 52. But you want to make a note of where it came from. That came from the manufacturing section. So I'll slice it off. There's a total of how many things? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a total of 20 items that I have to do this with. Notice that the sample sizes between wholesale and manufacturing are both 10. So I don't have one sample size smaller than the other here. So either one of these samples could be connected with N1 versus N2. So I've got my 52. Now let's go and see if I can find all of the rest of the numbers. I think the next one on the list is 54. And that's once again from the manufacturing section. Then it looks like 56 is my next. Also from the manufacturing section. Let's see, 58 after that. And that's also from the manufacturing area. What else do we have? 62 up there. Oh, that comes from the wholesale. Since I don't want this data to disappear on me, I'm going to continue then another column so I can see it. So I'm going to do columns of 5 each, I guess. My next after 62 is 64, and that came from the manufacturing sector. Got it. After that, I got a 65 from the manufacturing sector. And it looks like I got another 65. That one came from the wholesale. After 65, then I have 66. That comes from wholesale. After 66, we got 67, comes from manufacturing. And let me start another column then. After 67, what do we have next? 69 comes from wholesale. Got it. After 69 comes 70, also from wholesale. After 70, I see a 71 from manufacturing. After that, I see a 72 from wholesale. After that, I see a 73 from wholesale. And then let me move on to the final one. 74 is what I have next. And I actually have it twice. I have 74 from the wholesale and 74 from the manufacturers. So let me slice those off. Then I have a 76, which came from manufacturing. Slice that off. Then I got a 77 from wholesale, and then an 80 from wholesale. So as I look through these numbers, you can see that the M's kind of dominate the early times, and the W's seem to dominate the later times. So if I had to guess, I think that it's possible that the W's are being paid more, but this is a two-tailed test, so we just want to know if it's different. Now let's rank them. Now what you want to do is you're going to have a ranking from 1 to 20. So those are my rankings that are available, and I'll just write them next to these numbers as I use them. Now the only time when I'm going to have an issue is when we have repeats. Right here, 65. Now for 65, I've got a 7 and an 8. If you take 7 plus 8, that's 15. Divided by 2, you get 7.5. So we take the average. And I'll mark those off. All right, continuing on. Next I can get to 9, then 10, 11, 12, 13, 14, 15, 16. So I was able to get all the way to 16. So I was able to go all the way to 16. However, I have a pair here that are the same. So I take the average of 16 and 17. Let me give myself a little space here. The average of 16 and 17 is 16.5. So I'll mark 16 and 17 off. And the rest, I think 18, 19, and 20 work out as they should. Now, as I mentioned, N1 is the same as N2, which equals 10. So it doesn't matter which one stands for N1 versus N2 is all I really care about. Just pick N1 to be associated with one of them. I guess I will associate N1 or 1 with the W's. So I'm going to associate N1 with the W's, just to pick something. Now let's go ahead and get our R. That means I want to add up all the rankings for the W's. And so as you start, my first one here occurred at the 62. So we're going to start putting these numbers in. 5 plus, where's my next one? 7.5. After that, then I have a 9. Then I have an 11 and a 12. And 14 and 15. And 16.5. 19 and 20. Now I want to make sure that it's actually 10. You got to be careful. Whenever I get overwhelmed with data, it's possible for me to miss it. So let me be careful about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this turns out to be equal to 129. Now let's get the other things that I need. I need mu sub r. That was N1 times n1 plus n2 plus 1 divided by 2. n1 is 10. And so that equals 105. And I also need sigma sub r. Here is the square root of n1, n2 times n1 plus n2 plus 1. All of that divided by 12. So this will equal the square root of 10 times 10 times 10 plus 10 plus 1 divided by 12. And let me go ahead and let my calculator do all this for me. So I can do 10. I'm sure you can do 100. But 10 times 10, I'm just going to do it so I don't have to do any computations at all. You don't even have to put a times after the next 10. You can just start the parenthesis. So I'll have 10 plus 10 plus 1, end the parenthesis, and then I divide by 12. You don't have to get outside of the square root for this. Just hit enter and see what we got. So I get 13.229 to 3 decimal places. So that's my sigma sub r, and this is my mu sub r. And now we're ready for our test statistic. Z equals r minus mu all over sigma. So you can see this takes the same form of when originally I don't want to say years ago, but whenever you had stats 1, you would have had to normalize things to use the standard normal distribution table. This is identical to that stuff. Let me put in my numbers. We have 129 minus 105 divided by 13.229. And let's see what we get for that. I'll put parentheses around my numerator. 129 minus 105. Finish that off and divide by 13.229. I get about 1.81. You only need 2 decimal places for this, so approximately 1.81. Now let's get our critical number. This was a two-tailed test. Let me see what alpha originally was. Alpha was originally 0.10. So alpha equals 0.10. We want to divide alpha in 2, so we get 0.05. And remember, this is a normal distribution. So we're going to have 0.05 area out there and 0.05 area inside of there. And I don't need to use a table or anything for this. I can use my calculator, use the inverse norm to get you the x value. Since I'm looking for critical numbers, I want to use the inverse norm. So let me go to distributions, choose number 3. If I hit this left one, then the right one will just be the positive version of that. So I'm just going to put 0.05 here. Let me enter my way through and see what my left one is. I get to, well, it's negative 1.645.
And let's take a look at our number that we came up with, and we can see that it is in the critical region, so we reject H0. So we do believe there's a difference in the way they're paid. Another example here, if you look at this, since we're talking about before and after things, before and after samples, we have dependent samples. So for this one, we use the signed rank test. All right, well, let's go ahead and do that. Now, this is a little bit different than what we did before. What I think, let's get our H0 and HAN first. And then we'll go ahead and get all the information in. All right, so we want to know if an experimental medication affects an individual's heart rate. The physician randomly selects 15 patients and measures the heart rate of each. The subjects then take the medication and have their heart rates measured after 1 hour. So let's take a look here. Can the physician conclude that the experimental medication affects an individual's heart rate? It doesn't say whether it's supposed to go up or down. It just says that whatever it was before is different than whatever it was after. So we can do this. I can say there's no difference in before versus after heart rates. And of course, the second one would say there is a difference. In before versus after heart rates. They didn't say lower or higher or anything like that, so we've got to take what we can use, and this looks like it's going to be a two-tailed test. All right, first, remember what we have to do is organize these things and then rank them. Let's get our befores and afters. Now, unfortunately, I'm going to have to keep moving the page up and down as I go, but let me get as many before and afters as I can. So I'll have a 72, then I'll have an 81, 75, 76, 79, 74, 65, 67, and then the second of those, 76, 83, 66, 75, 76. Try to memorize enough of them. And then we have 78 and 68. And now let me get the afters. We got 73, 80, 75, 79, 74, 76, 73, 67, 74, 77, 70, 77, 76, 77, 76. I think I saw 75 and 74, but I'll recheck those. Yes, I did. Now let's take their difference. So I'm going to have negative 1, 1, 0. Remember, we're not going to count zeros. Negative 3, 5, negative 2, negative 8, 0, 2, 6, negative 4, negative 2, 0, 3, negative 6. Now let's take the absolute values of these things. Now let's rank them. Now we do not have rankings for the zeros. So let me find any zeros and take them out of the possibilities. Now there were, I think, a total of 20 of these things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, sorry, 15. So we have 12 of them that will have a rank. So remember, when you start doing this, write up your numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. All right, so I see that I've got a 1 and a 1, so they're repeated. So those ones are going to take up spots 1 and 2. Now 1 plus 2 is 3. If you take 3 divided by 2, you get an average of 1.5. All right, next, let me see if I've got any 2s in my list. It looks like I have 1, 2, 2, 2, 3 2s. So now I want to take the average of 3, 4, and 5. So if you take 3 plus 4 plus 5, you will get 12. Divided by 3, because there's 3 numbers there, and you'll see that you end up with a ranking of 4 for each of the 2s. Now let's mark those numbers off. Now I'm going on to 6. There is 1 3 here and another 3 here. So the average of that would be, the average of 6 and 7 is 6.5. So I'm going to put a 6.5 here and a 6.5 here. So let me cancel those out. Now what's next? Do I have any 4s? I do have a 4, and it gets an 8. Let me mark that off. Now, do I have a 5? I have a 5, and it gets a 9. Got it? I got 2 6s. So they've got to take the average between 10 and 11. The average of 10 and 11 is 10.5. So 10.5 here and 10.5 here. And then the 8 will get the 12th spot. Now let's take a look at our signed rankings. So remember, it's going to take a negative for these when the difference is negative there. So I'm going to have a negative 1.5, and then I'm going to have a positive 1.5, and then I'll just go down. Negative 6.5, get a 9 there. Negative 4, negative 12, positive 4, positive 10.5, negative 8, negative 4, positive 6.5, and negative 10.5. Now let's take a look at the negatives versus the positives. So the negative values, let's put those all together. I'm going to have negative 1.5, negative 6.5, so negative 1.5 minus 6.5 minus 4 minus 12 minus 8 minus 4 minus 10.5. This looks like a plus 2 here, so I'm going to fix that to make it look like minus 12. Let's pull up the calculator and let it do this for me. Negative 1.5. Remember to use the negative for that, and then you can use minus for the rest of it. Minus 6.5, minus 4, minus 12, minus 8, minus 4, minus 10.5, and I get negative 46.5. Now let me get the positive values. So I have 1.5 plus 9 plus 4 plus 10.5 plus 6.5. And let me go and use my calculator for this. So 1.5 plus 9 plus 4 plus 10.5 plus 6.5. And let's see what we get. 31.5. And now our test statistic is going to look like this. This is W sub S is going to be the minimum of the absolute value of the W minuses versus the absolute value of the W pluses. So that will be the minimum of the absolute value of negative 46.5 or the absolute value of 31.5. And so take those absolute values, and we're going to look at the minimum of 46.5 versus 31.5. The smaller one is 31.5. So that there is my test statistic. Now, let's take a look at our alpha. Let's come back up to find out what that was. That alpha was 0.05. Now, for the table we're going to use, we can simply use the two-tailed test. What was our n? N equals, well, remember, this n has to be manufactured first, has to be made up of the non-zero items here. So if we look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n is 12. And let's go ahead and pull up the table. The rank sum, or I'm sorry, the signed rank table. Let's take a look at it. We have n is 12. We're doing two-tailed alpha equals 0.05. And it looks like our critical number here is 14. So that comes straight from the table. So W sub 0 equals 14. So clearly W sub S is greater than W sub 0. Now remember, these things work a little bit opposite of our normal situations here. With these sign tests like this, this means that we do not reject H sub 0.